Welcome to this video on blockchain. This video was researched, written, and produced by Andrew Chapman and was read by OpenAI's text-to-speech model using the Echo voice. Blockchain is a decentralized, distributed ledger technology that operates as a secure and transparent method of recording transactions across a network of computers. Unlike traditional databases managed by a central authority, blockchain relies on a peer-to-peer network where participants, called nodes, collectively maintain the integrity of the data. Each transaction or set of data is grouped together into a block, which is then linked to previous blocks, forming an unalterable chain of records. This is why the system is called blockchain. The essence of blockchain lies in its decentralized nature, which ensures that no single entity has control over the entire network, making it highly resistant to tampering, fraud, or censorship. Each block in a blockchain contains three key elements. First, there is the data itself. The data recorded in a block can vary depending on the type of blockchain, but in a cryptocurrency blockchain like Bitcoin, it includes details such as the sender, receiver, and amount of currency transferred. For example, if Alice sends 1 Bitcoin to Bob, this transaction would be included in a block. Second, each block contains a cryptographic hash. A hash is a unique identifier that is generated by running the block's data through a cryptographic hash function, such as SHA-256 in the case of Bitcoin. This hash serves as a fingerprint for the block. If even a single bit of data within the block is altered, the hash will change dramatically, indicating that the integrity of the block has been compromised. This property of cryptographic hashing ensures the immutability of the blockchain. Once a block is added to the chain, its data cannot be altered without altering every subsequent block in the chain, which is virtually impossible due to the immense computational power required. Finally, each block includes the hash of the previous block. This hash connects the blocks together, forming the chain. The linking of blocks by their hashes ensures that any attempt to alter the data in a previous block would require the recalculation of every block's hash in the chain, which is computationally infeasible. The decentralized nature of blockchain is maintained by its network of nodes, which are the computers or servers that participate in the blockchain. Each node in the network stores a full copy of the blockchain, meaning they all have access to the same data and collectively validate new transactions. When a new block of transactions is created, it is broadcast to all nodes in the network. The nodes then verify the validity of the transactions, ensuring that they adhere to the rules of the blockchain. For example, ensuring that no double spending occurs in the case of cryptocurrencies. This process of verification is called consensus. Different blockchains use different consensus mechanisms to ensure that all nodes agree on the current state of the blockchain. The most common consensus mechanism is proof of work, POW, which is used by Bitcoin and many other cryptocurrencies. In a proof of work consensus system, miners, specialized nodes that perform computational work, compete to solve a complex mathematical problem. This problem involves finding a special number called a nonce, short for number only used once, that, when combined with the block's data and passed through a cryptographic hash function, produces a hash that meets specific criteria, such as a hash that starts with a certain number of leading zeros. This process is known as mining. Solving the problem requires significant computational power because the miners must try many different nonces before they find one that works. Once a miner solves the problem and finds a valid nonce, they broadcast their solution to the network. Other nodes quickly verify the solution by passing the block's data and nonce through the hash function and checking if the resulting hash meets the criteria. If the solution is valid, the new block is added to the blockchain, and the miner is rewarded with cryptocurrency for their efforts. This incentive system encourages miners to continue participating in the network and maintaining its security. The process of adding blocks to the chain in a proof-of-work system is designed to be resource-intensive and time-consuming. This difficulty prevents any single entity from gaining control over the network by rapidly producing blocks. The decentralized nature of the network, combined with the computational difficulty of mining, ensures that altering the blockchain retroactively would require an attacker to control more than half of the network's mining power. This is known as a 51% attack, and while theoretically possible, it is practically infeasible in large blockchain networks like Bitcoin due to the immense amount of computational power required. This high level of security is one of the primary advantages of blockchain technology. While proof of work is the most well-known consensus mechanism, it is not the only one. Another common method is proof of stake, POS, which seeks to reduce the energy consumption and computational requirements of blockchain networks. In a proof of stake system, validators are chosen to create new blocks based on the amount of cryptocurrency they hold and are willing to stake as collateral. The more cryptocurrency a validator stakes, the higher their chances of being selected to add a block to the chain. Unlike proof of work, proof of stake does not require intensive computational work to solve cryptographic puzzles, making it a more energy-efficient consensus mechanism. However, it still maintains the security of the network by requiring validators to act honestly. If a validator attempts to add a fraudulent block, they risk losing their staked cryptocurrency. Beyond consensus mechanisms, blockchain relies heavily on cryptography to ensure the security and privacy of transactions. Public key cryptography, in particular, is fundamental to blockchain. In public key cryptography, each participant has a pair of keys, a public key and a private key. The public key is openly shared and is used as an address to receive transactions. The private key, however, is kept secret and is used to sign transactions, providing proof that the transaction was authorized by the owner of the funds. When Alice sends 1 Bitcoin to Bob, she signs the transaction with her private key. Nodes in the network can then use Alice's public key to verify that the transaction was indeed signed by her and not someone else pretending to be her. This system ensures that even though transactions are broadcast to the entire network, only the rightful owner of the funds can authorize their transfer. Blockchain technology also introduces the concept of immutability. Once a block is added to the chain, it becomes extremely difficult to change the data within it. This is because altering a block would require recalculating the hash for that block, which in turn would require recalculating the hashes for all subsequent blocks in the chain. Given the computational power required to perform these recalculations, it is practically impossible to alter the blockchain once a block has been confirmed by the network. This immutability makes blockchain an ideal solution for applications that require a high level of data integrity, such as financial transactions, supply chain tracking, and legal records. In addition to its immutability and security, blockchain provides transparency and accountability. Every transaction on a blockchain is visible to all participants in the network. While the identities of the participants are pseudonymous, represented by their public keys rather than their real names, the details of their transactions are visible to everyone. This transparency allows for greater accountability in systems that require trust between participants. For example, in a supply chain application, a blockchain could record the movement of goods from one party to another, providing a transparent and tamper-proof record of the entire process. This level of transparency can reduce fraud and improve trust between parties who may not have direct relationships with one another. In conclusion, blockchain is a revolutionary technology that combines cryptography, decentralization, and consensus mechanisms to create a secure, transparent, and immutable system for recording transactions. Each block in a blockchain contains data, a cryptographic hash, and the hash of the previous block, ensuring that the entire chain is resistant to tampering. Nodes in the network work together to validate new transactions and reach consensus on the current state of the blockchain, using mechanisms such as proof of work or proof of stake. Cryptographic techniques like public key cryptography ensure that only authorized participants can initiate transactions, while the immutability of the blockchain ensures that once a block is added, it cannot be altered without enormous computational effort. Blockchain's decentralized nature and high level of security make it an attractive solution for applications ranging from cryptocurrencies to supply chain management, voting systems, and beyond.